Okay, here we go.
We are going to look at starting our next unit, which is the last one we'll finish this semester. We'll probably just start a little bit of unit 4 before we get done with the semester, but this one's going to take a while. So this is applications of differentiation. So we're going to skip around in the book and look at some different types of applications. So we're going to start with something easy. We should be able to get this one done today. It's not like that much of a leap from what we've been doing, and then we'll end with really powerful stuff. There's a couple sections that are quite powerful, much more than you've done before. Okay, so 3-1. I've already been hinting at 3-1, I think. So I don't think this should be a shocker or anything. Yeah. So 3-1 is just looking at graphs and discovering local, and absolute extrema. You've done some of this in pre-calc before, but you used your calculator. How did your calculator do this? Well, it uses calculus.
Extrema, like A.
Extrema is plural. So we've got one of our few theorems. I said there's about 5 important theorems this year. You had first the intermediate value theorem. This is the extreme value theorem. In this chapter we'll look at the mean value theorem. And then there's like one other big theorem, the most important one later, but it's quite a ways away still. Okay, so the extreme value theorem, here's what it says. So it says if you've got a function and it's continuous, it's got to be continuous on a closed interval a to b. Then you know it's got a max and min on that interval. Let's look at some different pictures how this works. Extreme value theorem is real simple.
Can I ask you a question?
Already?
Yes, I said it was important. I forgot the intermediate value theorem, so I was going to say again.
Well, we'll go back and look at it later. Intermediate value theorem is use continuity, and it's what allows you to connect stuff. It's what says that if you have a continuous piece of a function and you have an x value in that area, there's got to be a y value for every x value in there. It's just that idea that it's like connected. That's what the intermediate value theorem says. This focuses on the idea of there's got to be maxes and mins if you meet the criteria, right? If you meet the hypotheses. So let's look at some different pictures. So how about this? So there's my 3 examples to illustrate this theorem. I don't think this is hard. This is a really easy theorem. Okay, so do we have both a max and a min on this one?
Yes.
I think so. Is it continuous?
Yes.
Yeah. Is it closed?
Yes.
Therefore, we know it has to have a max and min on that interval. What does it look like the maximum is?
That
The peak? Yep. So the max here looks like the peak. What do we call that thing? Cusp? Yeah. Looks like a cusp more than a corner, except we got curves on it, right? So the max is a peak, and the min
is at A.
at A. So the min value, this is a distinction which we're going to have to be careful with. If it's asking you where something is, I've said this before, but if it's asking you where something is, they want A. But if they ask you for the minimum value, they want
Arrow
F of A.
Why'd you draw an arrow?
And like on the AP exam, if you gave them one when they asked for the other, then it's going to be completely wrong. So you got to be careful. What's up? I don't know. I drew an arrow because I did. Nothing special. Okay, this one. Min and max. It's not continuous, right? This guy is not defined. How about if I do that to help you out? It's still not continuous. Does it obey condition 1? Does it exist? Let's call this point
Yes,
C.
it does exist.
Does it exist? Yes, it's that, right?
But
Does
you
the
have to
limit
put
exist?
some your thing.
Yes, the limit is that, or that value. But it doesn't equal the limit. The point doesn't equal the limit, it's not continuous there, therefore it doesn't satisfy the hypotheses, which means, does this have a maximum, by the way?
Yes.
Yeah, it does. The maximum looks like it's up here. But the theorem says that if it satisfies those hypotheses, it has to have both a maximum and a minimum. This one doesn't have a minimum, does it? Like, you could get really, really close to this guy and you'd be close to the minimum, right? But there is no way to actually get, if you actually could get to that guy, yeah, that would work, but we can't, it's open, right? So you could get really, really close, but how do you know when to stop?
You don't.
You don't, you can never quite get there, so there is no technical minimum value, right? All right, how about this one? Is there a minimum? Is there a maximum? You could never quite reach this guy, yeah? Maybe that point is there, but you can never quite get to it. So you can keep getting closer and closer and closer and closer, but you're never going to quite get a maximum value. If I come along and say, let's say this hole is actually at 10, okay? So let's say this hole is at a y value of 10. If you come along and say, well, I think I know the maximum value. I think it's 9.999. What am I going to do? Exactly. I'm going to say, well, 9.99999 is bigger and it's still on there. You're going to say,
9.99999.
It's gonna go on forever.
Repeton.
okay, so that doesn't satisfy the hypotheses. I thought the theorem said if you had certain things that you'd get a max and min. Well, we got a min, why did we get a max? Is this theorem wrong? That's continuous.
It's open, but it's on.
It's an open, it's a partially open interval. This is A to B like that. It doesn't meet the hypotheses, right? So as long as it's a closed interval and it's continuous, you know you have to have a maximum or minimum. Now, what kind of maximum or minimum? I think that there's a little bit of a difference. There's local ones and there's absolute ones. So let's talk about that. Some problems require you to find only a local one, depending on what the constraints of the problem are. Some problems want you to find an absolute one, so we need to be able to do both. So let's do a quick definition. I think we've seen that word local before, haven't we?
In the neighborhood.
So we call relative or local extrema, it's the same thing. Critical points, this is big. I'm sure they'll ask you this on the exam in certain places. A critical point is a local or relative extrema. Those are all the same things, okay? This is like a theorem and a definition all in one, kind of. So it tells you what they are, and it also tells you where they are. Where do local extrema occur? So if I have like a polynomial, let's think about a polynomial. You know what, let's put a sharp corner on it too. A couple sharp corners.
What is that function?
Here.
I don't know. These guys are local extrema. They're local because they're only extreme in that small neighborhood, right? This guy's only a maximum as long as you're in that neighborhood close to him. This lady's only a minimum as long as you're in that neighborhood close to her. So they're local, right? Let's say I stop this up here. Now that's the absolute maximum. If I stop this right here, that guy's the absolute minimum overall. Okay, that's the difference between local and absolute. How do you find these guys? Can you guys help me out? The corners are still local extrema, aren't they? Just because they're
Well,
corners.
if it was in
I
your
think they still
calculator,
are.
you could
Right, but
Sorry, didn't mean to be so loud. Can I ask you a question? Do you know how I can get to the golden boy? Austin, maybe you could help me?
I'm not sure exactly what it is.
Maybe you should ask Austin about that. Just saying. Thank you.
well, I guess we'll have to follow that up later. I'm
When the
interested now.
camera's off. When the camera's off, we'll talk.
Okay, so let's think about calculus. How can we find these things? For instance, what's special about this point in terms of calculus? Think of derivatives. You can make a tangent line at any point, though. You're on it, though. What's special about that tangent line right there? What would it look like?
Wouldn't it be like, yeah.
It'd be like that, right? And this one would be like that.
You don't,
And this one would be like that, and like that.
So it's when the tangent lines are zero.
What?
The tangent lines are zero.
Oh, so you're telling me that these points have to occur where? Give me the symbols.
Where the slope of the tangent line is zero.
That's the slope of the tangent line.
Yes.
Okay. What about those other ones? I thought those corners were relative or local maxes and mins too.
Or
No
where
tangent line there.
they,
What's true about the derivative there? There's no tangent line. That's true. But the derivative,
It wouldn't work,
the derivative does not exist there. So they occur either where this happens
where
or where f prime of x does not exist. So I think all we have to do to find those things is calculate a derivative and check those two things, and we'll be able to find any possible maxes and mins. It's pretty nice, isn't it? So that's what your calculator does. And the point is, the calculator can't do this in all problems. What about those implicit ones that had x and y in it? Did you do those with your calculator?
But once you work those out, like once you got it down to it, couldn't you put your calculator? Like after you solve.
Some things you cannot solve for explicitly, it's impossible. But you can still do this. In fact, a lot of things you can't solve for, it's impossible. So you still need to be able to do this with a lot of things. So let's look at a couple examples. So example one, let's try to look at this guy. And notice, don't we want to probably talk about a specific interval usually? I think usually we're only interested in the part of the number line. So let's talk about that guy here. -1 to 2. So I want to find all the maxes or mins, and then I'm going to also talk about which one is the absolute. Okay? You guys tell me, this is what kind of function? It's polynomial, right? Polynomials are always continuous, so the extreme value theorem is going to apply, isn't it? It's closed. That guy's got to be continuous everywhere. So we know there's an absolute max and min on this interval that has to be there. So let's find it.
So once you start by finding f.
Yep. So I'm going to find f prime. It's going to be easy on this one, isn't it?
So x3.
And then we do what with f prime?
plug it in.
Make it zero.
Make it 0. So those are the places where we're going to get a horizontal tangent line, but now we're thinking those are also the places where we're going to get our maxes and mins, right? So then we say, oh, that's an easy equation to solve. Look at that. What can I factor out?
12x squared.
If I do that, what's left? Okay, so I think our local maxes or mins are at what? I think this guy gives me x equals 0 as a critical point, and this guy gives me x equals 1 as a critical point. Sweet. Do we need to check if it's undefined? Look at f prime. Is that undefined anywhere? No, it's polynomials. We're done. Okay, so the only question is, are these maxes or mins? What are they? So we know they're critical points right now. We don't know what they are. So I think to decide what the absolute maxes or mins are, we better check. Let's just make a little table. So let's check these x values and see what we get. Right? Am I putting f prime here?
Nope.
I want to see like how big they are in the original function. That's the point, right? Alright, so I'm going to check 0. I'm going to check 1. Those are both in this interval, by the way, aren't they?
try
I think I need to check something else too.
negative 0.5.
That's not a critical point, is it?
No, but
It's a what? An endpoint. If we think about the way this could possibly look, the absolute max or min, if we have like a polynomial like this guy, right? Something like that. This guy's to the 4th degree, so let's make it go like that. More realistic, right? We found a couple critical points, things like these guys, right? But if we cut it and say, okay, stop it right there, and stop this one right there, where else could the absolute max or min occur? Could happen at one of these guys. Could also happen on
so
the
you need
edges.
to check two.
So you have to check the edges too, right? So we're going to check the edges, -1 and 2. We're just going to see which thing's biggest, which thing's smallest, and we're done. That's all we got to do. That's easy. We put 0 in. That's 0. I put 1 in. That's right.
You're gonna put a negative 1?
I put 2 in. 48 minus 32 is.
It's not.
No what?
Oh, it's something minus 40.
Okay, this guy I'm going up with 2, right?
Yeah.
So that's 48 minus 4 times 8 is 32.
Yeah.
You just put it there, Sinead.
Now,
-1. Even's going to be positive, so that's 3.
Plus 4.
That's going to be 7.
So that's your.
Okay, so we just found out the absolute maxes and mins.
It'd be 16 and
Absolutely.
1.
Okay, so let's write this the correct way, just so we know what we're talking about. They could ask you different things. We know that they happen right there, right? So we could say this is the absolute max of f of x, where?
In interval.
Because that guy has no absolute max unless you specify on the interval exactly. Thank you, Mr. Guardino. And is 16 and occurs at x equals 2. Okay, now they could ask you, I might just ask you what's the absolute max, you know, or what's the,
Yeah, because that's a lot.
pay attention to what the question's asking. Okay, you don't have to write that out every time. Just say whatever the question has to do with. And then this guy could write out the same thing, that's the absolute min. Those other guys are just, this guy was a critical point, that's like a local max or min, etc. Okay, let's do another couple more examples. So we gotta check those endpoints, don't forget your endpoints. If you're looking for absolute extrema, you need the endpoints. Now, if they just say find the relative extrema, do you need to check the endpoints? You do not.
I don't want to be really costly meetings we have here. I didn't see anything. It's like I turned to and closed my eyes.
Weekend.
Everybody's looking forward to the.
Okay, we're gonna do 2 more examples. Here's this one. So here's a trig example, trig functions. What are we gonna do first? Same question. I want the absolute maxes and mins. Okay, what is it?
2 cosine plus sine 2
Okay, let's one at a time.
I love it. People are starting to rearrange in their heads. It's just going to be so useful to them. Okay. Now, I'm going to set that to 0, right? I don't think it's going to be, these are sine and cosine waves. Do you think it's going to be undefined anywhere? I don't think so. We don't have to worry about that, but we do need to know where it's 0. Remember when we had equations that mixed trig functions, what do we usually have to do? You have to change one into the other using some kind of identity. What's an identity here that comes in handy? I don't think we can do anything with cosine, it's just cosine, right? Is there any identity for cosine? No. There's a nice identity for this one, double angle. It's 2 sine cosine. Isn't it? That's a nice identity, we know that one. I don't think there's gonna be any real sneaky identities they're gonna ask you about this year, but that one might be. Okay.
Pull out a 2 cosine.
I can pull out a 2 cosine x and factor now. See, I can go 2 cosine x, pull that guy out, what's here, 1. If I take those parts out, that's a plus 2 sine x.
So how do you know that equals 0? Like on the last one, how did you know that the thing at the beginning equals 0?
What are you trying to do?
That's what we're doing right here.
We're trying to find the critical points, and that's where we look where the derivative is equal to 0 because of that idea, this idea, right? So I introduced that. It wasn't natural. I said that's what I'm trying to find. Okay.
Pi over 2
So this says where is cosine of x equal to 0 and where is sine of x equal to negative 1/2? On this interval only, right? We're not looking everywhere. So where is cosine 0? Cosine is the x's. That's here and here. So we've got x equals pi over 2 and 3 pi over 2. So we better get a chart going over here. So I'm going to check these guys. Got to check the ends, right? So 0. Well, I better finish this up. Okay. Can you guys help me with this one? Sine of x. Where's the y value negative? Isn't it down here? Negative 1/2. That's how many degrees?
Yeah.
And also over here, it's going to be negative, isn't it?
So 11 pi over 12.
Over 12?
Oh yeah, 11 pi over 6.
That's that one, right? Now, you guys tell me, is this negative pi over 6? Yes, it is, right? But what's the problem with negative pi over 6?
It's not there.
It's not there. It's not where we need to check.
Wait, how
okay?
many degrees is that right there?
30.
So you're
This guy is how many?
7 pi over 6?
Thank you, Anna. 6. One more, 7. Okay. So we've got those. I think we need to add all those things into our list. So 0, what's next biggest?
Next. Oh,
Three, why did you do 7 pi over 6?
because that's the one over there.
I thought you were doing 3 pi over 2.
No, that's for the sine.
Oh, that's for the sine. Oh,
Two separate factors, right?
Okay, yeah.
Okay.
Well, there just was an error, so I got confused.
So we got a lot of them to check this time. Ooh. Notice I also have my edges in there, right? Didn't forget about my edges. Okay. So where am I testing these? Be clear, remember, this better be labeled correctly because we'll be doing different things. Sometimes we might put F prime here, sometimes F double prime. And label it clearly. We're trying to find the max or min of F this time. So I'm going to put 0 in. Okay, sine of 0 is 0 minus cosine of 0 is, what's cosine of 0? 1, right? So that's a negative 1. Okay. We might need to do a bunch of scratch work on this. Let's just see them. Okay, pi over 2. That's 2 sine of pi over 2.
Wait, which we gave for the first one? We're gonna have to get x equals,
You're talking here.
yeah,
What
would it
is
be,
It would be a negative 1 because cosine of.
would it be 1/2? Because you have to multiply by 2.
No, because he's doing the original.
Yeah,
It's
yeah,
not.
that's a 2x.
Cosine of 2x.
It's 0 times 2, which is 0.
Oh,
which is
0.
cosine of 0.
Good question. Thank you, Todd. I'm sure several of us had that one. So
Over 2 is 1, so that's 2 sine of.
what's 2 times pi over 2 is just pi, isn't it?
So it's 2
Okay,
minus-
so I'm going to give you guys a second. Work these out. Work these out. We need to do these. Sounds like we're struggling a little bit.
Pi over 2.
I'll do the second one for you, but that's okay.
So
X is Y, so 1. Well, let's say 1 times 2, so 2. 2 minus.
Okay, so you have the cosine of pi.
I'm pretty sure I memorized it in the test. Like when I was putting out the information.
Austin, are you doing these?
Yes.
Oh. You can't do them quick?
Can't.
Write them out, then it's fine.
I'm so bad. Like,
Write it out. If we had our calculator, could we put these all in our calculator in radian mode?
Yeah.
Might be a good way to go, right?
So we can do that?
Didn't say you couldn't. We should be able to do them without it. You're certainly going to have parts on that test where it comes up where you need to be able to do these by hand, but I think we can all do these. It's just a matter of whether we're faster or slower at it.
I just don't.
So I'm going to do the ones I like
I'm 5 or 6.
with
I'm
by
trying
hand,
to
and then do the other ones with my calculator.
I just don't know what's what. Which side's which. You know what I'm saying? It's more than pi, so. Like, it's not like where it is, it's just like I didn't
learn some negative 1, 2, yeah. Remember that stuff.
I don't want to do that one.
It's 11 pi over 3, which is negative 3 over 3.
I think so. Yeah, I don't want to do it though.
I don't want you.
2 sine of
Oh, I should No, I got that for
I forgot the trick.
Can we do this in our calculator? Somebody give me one of those in the calculator, one of those other 2 that I didn't do yet?
I got 1.5, negative 1.5 and negative 1 plus 3 over 3, but
I think one of those is right. Check yourself.
So I have
Should
a
be
question.
take just a second in your calculator. Make sure it's in radian mode, right?
What was the
Let's do these 2 with our calculator.
how we like figure out where like those triangles are on the unit circle, like 7 pi over 6, like you go like the 6th and the 12, like how do you do that?
I think about it in terms of pieces of size 6. So this is pi, which means there's 6 pieces of size 6, and then one more is 7. So there's my triangle right there. And I say
So
pi
like
over 6
2
is-
pi would be like 12. Like if you went all the way around once,
Yes,
you do 12.
yes, yeah. So that's where your 14 would be like 6, 12, a couple more right there.
negative 1
Okay.
is the 7 pi
I
over 6,
never
right?
read that. That makes it so much
You got
easier.
negative 1/2?
Yeah. I just had
I don't know, I think I got negative 1.5.
That's what I had the first time.
But you only had that for one of them.
I know.
What we got? Somebody help me?
Negative 1.5 and negative 1.5.
These are both negative 1.5 if you do it correctly. Okay, but we could use our calculator, and on the exam, are we going to try to do these by hand if we have our calculator? No. Okay, so I think now we know the absolute maximum. What's the absolute maximum value this function attains on this interval? 3. What is the the absolute maximum value is 3, it happens at pi over 2. Okay. Where does the absolute minimum value occur?
7 pi over 6 and 11 pi over 6.
It happens twice, and it happens at those 2 places. That can happen. If we did this on our calculator, that's exactly what it would give us. Okay, one more, shorter one. Okay, that guy. Okay, if I specify on negative infinity to infinity, does the extreme value theorem guarantee an absolute?
Volleyball team at this time. Please release the volleyball team at this time.
So we interchange.
I think there's one like this in the book, Riley, so just have a look at it. It's pretty good. Yeah, it is. Good luck. Okay, this one I don't think is going to be very bad. We're just going to do the same thing, right? Take the derivative. What do we do? Bring down the 4/5, leave the stuff inside alone to the negative 1/5. I don't really have any chain rule here, do I? Times 1. So I'm going to set that equal to 0. Let's rewrite it because I think we really need to.
5/5 root of
And that's 1/5 is the 5th root, like it was saying. Quantity x minus 3. Are we okay with that? So you guys tell me, does that equal 0? This implies that 0 equals 4. You just look at the top, right? A fraction is only 0 where the top is 0. That can't happen. There's no critical points because of that.
So does that one
So I need to look at the does not exist thing, right? How could this does not exist? You look at the top for setting it to 0. There might be like a cusp or something, exactly. So how would I look for that? It's going to not exist if what happens? If the bottom is equal to 0. So if I set the bottom equal to 0, that's going to tell me where it either has like an asymptote or a cusp or something like that. Okay, so if I just divide, that goes away, right? And you just divide by 5 on both sides of an equation? Yep.
Also,
You can 5th power on both sides of the equation, yep.
X equals
I think it is undefined at x equals 3. What is undefined at x equals 3? The function or the derivative? The derivative is undefined, which means the function has a what there?
a hole.
No, a cusp or a corner.
It has, the main point is that it has a max or min there. Let's look at this guy with our calculator. So this guy is a max or min. It's a critical point, okay? This is a critical point. So we got to be careful about that. Don't forget the does not exist thing. You put your critical points there too. If we put this in our calculator, what's it look like? Let's do it. You guys put it in your calculator, put it in FX. Have a look at it.
That's what she says. It is.
What song is it?
So I dream.
What did you say?
I was just thinking it was Susan Boyle sings. Did you get? You already grabbed it.
I think it's a cusp, but I kind of predicted it. Yeah. So, is that thing?
Oh, that's
What is
oh
it?
my God.
So you guys give me a little bit more. It's a what?
A minimum.
What kind?
Absolute.
It's absolute. Looks like to me. Absolute, and it's
That's
also.
oh my God.
Local.
So that guy's an absolute and local. Isn't it? You didn't get that, Austin?
No.
What'd you put in your calculator?
I think I missed a pair of parentheses. I only had one pair of parentheses on the bottom, but I think I need to have it around the whole thing.
I think you on your calculator you go like,
Oh yeah, that's what I did.
that's key.
I
Graphing
grabbed
the
the
original
derivative,
function.
That's what I just do two rather than do the alpha.
So one key in this chapter is gonna be when are we looking at a derivative, when are we looking at a second derivative, when are we looking at the original? That's the thing. Yeah, you have to use the thing you need to use.
Just like stats when you're changing things to make them straight.
Yeah, I think it's gonna make more sense in here.
Yeah, that was a lot. I know it's a lot more organized to see.
Okay,